and where, I have to figure it out. I'll let you know. We'll just do something on Monday. Okay, so just to quickly review what we were discussing, because we rushed through it, or at least we, meaning the royal we, rushed through it at the end of last lecture. We saw the fine structure of hydrogen. For the first excited state, through principal quantum number 2. So what we have in the absence of our relativistic corrections was an 8-fold degenerate manifold of states with 2s orbitals and 2p orbitals. And the good quantum numbers here were n, l, m sub l, and m sub s. S is, of course, also a good quantum number. Okay? And then we added in the relativistic corrections, which came in the form of the corrections to the kinetic energy and relativistic field corrections, particularly the Darwin term that affects the coupling of the electron and positron, and then magnetic effects. Magnetic effects relative to electric effects can be thought of as relativistic effects, but we can just think about them as magnetic effects as well. And what we found is that if we just thought about the magnetic effects first, that what we saw was that we get a splitting here with a new set of quantum numbers and a new notation that we reviewed, where, so this is due to the spin orbit. Which is a magnetic effect. And the new good quantum numbers arose because the spin orbit, that is to say the orbital angular momentum and spin angular momentum, are coupled together. So the new good quantum numbers are not m sub l and m sub s, which are the uncoupled representation, but now we have j and m sub j. So with the spin orbit effect, let me just we have the coupled representation. That's the good quantum number, where we discussed and reviewed last time that we could think of a state with a good total angular momentum and projection of total electron angular momentum along a given quantization axis as a superposition of the uncoupled basis weighted by the Clebsch-Gordan coefficients. And the Clebsch-Gordan coefficients tell us how to add angular momentum, and they satisfy a set of selection rules, right? The total angular momentum J can be between L plus S and the magnitude of L minus S, and the magnitude M sub J must be equal to the sum of M sub L and M sub S. So here J is the quantum number associated with I typically write my J's in units of H bar, so I don't typically write the H bars in. So we were able to just diagonalize the spin-orbit interaction by just noting, recognizing that this operator is a simultaneous eigenstate of this operator associated with coupled angular momentum. Okay, so this notation over here, when we're thinking about an electron orbital, one in the context of including spin orbit, then instead of writing just the N and the L, we also write the J. So this is an orbital that involves spin, but spin and orbit couple, and these quantum numbers are typically written as N, L, J. That's what this notation means. Okay? And then the S is, of course, a half, and the M sub J, well, these are degenerate states. Of course, the L equals 0 doesn't have a spin orbit coupling, but the L equals 1 does, and I can add a half or subtract a half, which is why J is either 3 halves or 1 half. Now, in the context of hydrogen, where we have this, or hydrogenic atoms, where we have a 1 over R potential, where we had this degeneracy in L, there's this nearby S orbital as well. And we need to think about the actual splitting, we need to think about the other relativistic corrections, the Darwin term and the relativistic kinetic energy. And we found that when we put all that stuff together, that this stuff shifted, and these guys shift together, and we have this plus Darwin and relativistic kinetic energy. And this is a reflection of the fact that the in the hydrogen atom, we still have this degeneracy because of the nearby L orbital, and at the end of the day, or S orbital, the energy only depends on the J quantum. So this is now degenerate. Now that's not exactly true, because if we really wanted to sort of look at this kind of scales that we're looking at here, where this splitting here is of order some gigahertz, then we have, in addition, a splitting. I mean, these guys get shifted a little bit as well by the Lamb shift, but most importantly, there is no longer a degeneracy between the 2s 1/2 and the 2p 1/2, and this is what we call the Lamb shift. Okay? So this is what we call the fine structures of hydrogen. Now, one thing that that came up at the end of class that others were working, think about, doing atomic physics with the spectrum of other atoms. This near degeneracy of say the 2s 1/2 orbital with the 2p 1/2 orbital is just not there at all. This is something, again, I want to emphasize. This near degeneracy between different L's for a given principal quantum number is only true for one electron atoms. If I have many electrons, I don't have a 1 over R potential anymore seen by the electron, because it's one of the electrons sees the potential of all the other electrons and the proton. And that totally changes the whole nature of the game. In fact, the splitting between the 2s and the 2p in sodium or lithium is about the same order as the splitting between the ground state and the first excited state. So we'll discuss that a little bit, but it's something that's often confused because we spend so much time talking about hydrogen that we think all atoms are like hydrogen, and they're not at all. okay? So we'll get to that. Of course, there's still the degeneracy in the M sub j. So there are 2j plus 1 different magnetic sublevels for a given j. And those would in general be split in the presence of a magnetic field. And that's one of your problems for homework, is to look at the so-called Zeeman effect that you remember is the interaction between the magnetic moment and an external magnetic field. Yeah.
So if you go to specify the wave function in terms of r theta and phi,
Yep.
is this the spherical harmonics are now in terms of j and j and j?
No, that's not correct.
That's not true?
No. The spherical harmonics are about the motion. They're not about the spin at all. So this is still a p orbital. So this is still, but in fact, it's a superposition of different p orbitals. So for example, let's look at an example. I wish I had Clebsch-Gordan coefficients off the top of my head, but I don't. Suppose I look at the 2p 1/2 state with a given m sub j. M sub j, of course, can be plus or minus a. Okay? So what does this mean? This means n equals 2, L equals 1, of course S is a half. And then J is a half, and MJ is a half. Okay. Now this itself is a superposition with coefficients that I don't remember, but with something with a n equals 2, L equals 1, L equals 1, n equals 1, S equals a half, M sub S equals minus a half, plus some other, I'll put the Clebsch-Gordan coefficient here. J, this is a half, 1, 0, a half, or 1, 1, minus a half. Okay, so what have I done? What I have done is I've taken the coupled representation and decomposed it into the product basis of orbit and spin, weighted by Clebsch-Gordan coefficients. These here are the radial wave functions, which are the same in this case, because L equals 1. No, sorry, here, this guy. And these are the spherical harmonics. So this is a y11 as a function of theta and phi. And this is a y10. But is a superposition of these. Let me talk to these gentlemen for a second. If I close the door here, can you do your work? Or is Okay, so that's, I'm glad you brought this up, Aaron. This is worth reminding what we're talking about here, because this is the kind of thing you need to do in your homework assignment. In order to calculate a dipole matrix element, the dipole moment of the electron depends on the motion, not the spin. So if we want to calculate a dipole matrix element between let's say we wanted to calculate something like this, right? This is an operator that is the charge of the electron times the position of the electron relative to the proton. And so to calculate this matrix element explicitly, we need to uncouple the states, write them in terms of the orbitals and the spins, and then look at the dipole matrix elements. Now we will see how tedious that is in this problem set. I mean, you know, tedium is hard to do in homework. But anyway, there is, at some level, a smarter way to do that. And we'll get to it when we review the Wigner-Eckhart theorem and the relationship between vector operators and matrix elements of states with definite angular momentum. We'll get to that in a few weeks. Does anybody have any other questions about that? Okay, good.
Why did you only take 2 states? I mean, is it just for examples? Or
These are the only 2 states that exist in this superposition.
yeah, right, you've only
Okay, because the L is fixed, L is 1, and the S is fixed, S is a half. And I look at a particular case where M sub j was a half. And we must have the sum of M sub L plus M sub S equals M sub j. So these are the only 2 states in the superposition which have non-zero foreign coefficients. Good question. All right. A question came up, I think it was last lecture, you know, we just got the time already, about what the heck about the proton magnetic moment? I mean, we had the spin orbit effect, which had to do with this spin of the electron. What about the spin of the proton? Well, so what we just discussed, what is called the fine structure, in particular the fine structure in hydrogen in the first excited state. What we want to talk about today is hyperfine structure. Okay, so what is hyperfine structure? Well, hyperfine structure is basically all the shifts of energy levels due to nucleus. Beyond point electrostatics, point particle electrostatics. So, say in hydrogen or in any of the hydrogenic atoms, we treat the nucleus as a point particle with charge Z times E, and then it creates an electric field, and that creates the binding of the electrons to the nucleus. Anything that has to do with the nucleus beyond that, we call hyperfine effect. So what are some effects? Well, we have the effect of the reduced mass, I should say beyond point particle electrostatics, point infinite mass particle. So remember we had this question about where the heck is the center of mass and the reduced mass. So anything beyond treating the nucleus as having infinite mass relative to the electron is part of hyperfine, what's called hyperfine structure, so the reduced mass effect, which we've talked about. There's what we had in our first homework assignment, which had to do with the finite volume of the nucleus. And then the most important effect in terms of the actual, these effects give rise to small shifts in the energy levels, but they don't change the basic symmetries, and therefore they don't change the basic degeneracies associated with the levels. However, the spin of the proton is the most important effect, or at least for lightish atoms, that can give rise. There's one other related effect here, which has to do with the spin, which gives rise to magnetic effects. But when we treated the volume of the nucleus in our homework assignment, we treated the nucleus as a sphere, right? So we still had spherical symmetry, and because we had spherical symmetry, we had still, all the same kind of good quantum numbers. However, when you start getting to pretty heavy atoms, then the nucleus starts to deform in shape, in which case we know if I have like an egg-shaped nucleus, well, it wouldn't just produce a electric monopole field, it would produce an electric quadrupole field. So there's a related effect here, which is the quadrupole. Effect. In fact, I made a big mistake once in a paper recently I wrote, because I never, not being a real atomic physicist, just playing one on TV, I never thought about the fact that atoms you have to worry about this. And when you look at strontium, I wrote a paper about strontium, and we forgot all about that until I gave a talk about it, and then, okay, thank God we didn't submit it for publication, because that would have been quite embarrassing. But it doesn't matter when you start getting to heavy atoms. But this is the dominant effect that we want to discuss today. Okay. So let's talk about the spin of the nucleus, or the spin of proton. Well, again, if I think about the proton as a kind of spinning ball of charge, then with the charge E, then it has a magnetic dipole moment associated with it. Now that's not right, because it's not actually spinning. It's just, we call it spin. So there's a fudge factor that we call the G factor that corrects for what the actual magnetic moment is compared to what it would be had it been a spinning ball of charge. Of course, if we have a fixed angular momentum, and the angular momentum of the nucleus is traditionally called I, then, so for the proton, I is a half, it's a spin 1/2 part. It's not an elementary particle, of course it's made up of quarks, and then how the heck it gets to be spin 1/2 is still kind of a mystery. I mean, it's some mix of what's going on with the quarks and gluons in there. It's one of the things that Professor Fields in our department studies. For a fixed angular momentum, the speed, the angular velocity goes like 1 over the mass. So the current goes like 1 over mass, therefore the magnetic moment is going to go like 1 over the mass. That's why the spin of the proton is less than the spin of, the magnetic moment of the proton is a lot less than the magnetic for a fixed angular momentum. So the magnetic moment of the proton we could write as the gyromagnetic ratio times the spin angular momentum, which is the G factor of the proton times E, the charge of the proton, h bar, over 2 mass of the proton, c. I is in dimensionless units, I in units of h bar. And this quantity is what's called the nuclear magnet. So what is the G factor of the proton? The G factor of the proton is about 5.6. Where that comes from, still a mystery, exactly. More generally, one often talks about a nucleus beyond proton. And one would write the magnetic moment of the nucleus as the G factor associated with whatever nucleus you have, whether it's a deuteron, the alpha particle, or the cesium nucleus, has its own G factor. Times the nuclear magneton.
Which are measured quantities, not calculated.
That's correct. Yeah. To my knowledge, I mean, I don't know anything about nuclear physics really well. I know something about nuclear, but not a lot. So I don't know exactly, but they consider measurements. And the spin of course, higher atomic number atoms is made up of the neutrons and protons. Neutrons have spin, even though they don't have charge, they still have magnetic moments. And so the spin quantum number of other atoms is not necessarily half. So for example, in cesium, the spin is 7/2, the standard non-radioactive isotope of cesium. Alrighty. So let's see. So now the question is, the fact that the proton has a magnetic moment means that there are magnetic interactions that with the magnetic moment of the proton that are due to the fact that we have this little magnetic dipole moment. And there are basically, so there are two effects. So magnetic interactions between the electron and proton spin. So there are two effects. Firstly, if I just think about this in a kind of, there's some orbit of the electron. Of course, the electron is in an electron cloud, but you can think about one particular orbit, and there's a probability distribution of all the orbits in the orbital. And then there's this proton sitting in the center here. Now, this electron creates a current loop. And that current loop makes a magnetic field. And that magnetic field then interacts with the little bar magnet that the proton spin is. So there's an interaction that has to do with the orbit of the electron with the spin of the proton, right? And we all remember from electrostatics what the magnetic field is for a current loop is, right? Maybe. Better study for your prelims. What is that? Well, I can think about this as making a magnetic moment. So the magnetic field, due to the electron motion at the origin, is twice the magnetic moment associated with this current loop due to the electron motion, divided by this radius, Q. So the magnetic field that, well, it's going into the board here, right, because the electron's got this negative charge, is interacting with the magnetic dipole moment. So the first effect, let's call this effect number 1, is minus mu proton dotted into this electron motion. And that is equal to minus 2 mu proton dot mu electron orbit over r cubed. This, again, in CGS units, the magnetic dipole moment has the same units as the electric dipole moment. It's charge times distance. So charge times distance, charge squared, distance squared, charge squared over distance is an energy. Dipole over distance cubed. If you want, there's a mu naught over 4 pi out front, but I don't want. Now what is the magnetic dipole moment associated with the motion of the electron? This is equal to, well, this is just the Bohr magneton times the orbital angular momentum with no g factor because it's just orbital motion. So that really is, there's no mystery. That's real spinning, meaning real moving charge. So that's what it is. And it's negative because the electron charge is negative. So this is then equal to twice the, or 4 times the g factor of the proton times mu b mu n over r cubed. Oh no. Well, where did I get that 4? No more there. Okay. There's no g factor for the electron. Okay. All right. So times the spin dotted into the orbit, spin of the proton dotted into the orbit. Okay. So that's one effect. For how how big is this term? What kind of perturbation are we talking about? Well, the question is, how big is this energy? So in atomic units, the Bohr magneton is like alpha times the electric dipole moment. This is always a useful comparison. If I have a charge and it's moving, and I want to know what's the electric dipole moment compared to the magnetic dipole moment, the ratio to them is the ratio of the speed to the speed of light. Okay, in CGS units. So that's this thing. Then we have the nuclear magneton is the same thing as the Bohr magneton, but there's a ratio. Remember, the Bohr magneton has the electron mass here, not the proton mass. So we just need to scale the electron mass over proton mass times the same thing again over A naught cubed. Okay, so what do we have here? Well, this is alpha, this is the mass of the electron divided by the mass of the proton times alpha squared times the Hartree. So this energy was related to the fine structure splitting. The hyperfine, at least this term in the hyperfine splitting, is reduced compared to the energy scale associated with the fine structure by the ratio of the electron mass to the proton mass. And that's about 1 over 2,000. Which is why this is not just fine, this is hyperfine. Okay? So this is what we call hyperfine split. right? So that's one effect that we need to consider. There is also an effect, which is the magnetic dipole moment of the proton, or nucleus more generally, is a source of magnetic field. That's to say, the proton is a little bar magnet. So it creates a magnetic dipole field. Okay, so there's the proton. And the electron is sitting somewhere. Of course, it has a probability distribution of being somewhere. And it's got some spin. And so there is an interaction between the magnetic field arising from the proton, which is arising from the fact that the proton has a spin, interacting with the spin of the electron. So, what is that? Well, the magnetic, so this interaction is the magnetic moment, the spin magnetic moment of the electron, interacting with the proton's magnetic field due to the spin of the proton at the position of the electron. Okay. Now, of course, there's another effect, which is the fact that the proton is moving relative to the electron, and the proton creates a current loop as seen by the electron, and that current loop in the frame of the electron interacts with the spin of the electron. But we already did that. That was the spin-orbit coupling. Okay? So that's a different effect. But we've already treated that one. And that term was of order alpha squared times the Hartree. There was no ratio of those masses there, because it had to do with the electron spin alone and had nothing to do with the proton spin. Alrighty. So what is this? Well, the magnetic field due to the spin of the proton is a magnetic dipole field, right? And that is equal to 3, the spin magnetic moment of the proton dotted into the radial coordinate minus u of the proton over r cubed. Just check something, right?
ER is just the unit factor?
Yes, E sub r is, I don't like to put r hat because r hat means something else. So I always use unit vectors with little e's, like out of Jackson's textbook. That's the magnetic dipole field, right? Remember that. And then this interacts the mu of the electron due to its spin. We just said it's minus twice the Bohr magneton times the spin. And the mu of the proton is the G factor of the proton, the nuclear magneton, I. So this effect is equal to minus 2 or 2g proton or magneton, nuclear magneton times S dot I minus S dot E sub R, I dot E sub R. Okay. Three, there's a 3. So now, okay, now it's okay. All right, so this, of course, is of the same order. It's of the order of the product of the Bohr nuclear magnetons divided by the distance cubed. So it's the same scale of energy. Now, this is actually not exactly correct. This is only true for r not equal to 0. When r equals 0, something funky happens. I mean, this thing blows up in a weird way. And in fact, if we thought about the nucleus having a finite radius, and think about the nucleus as being a uniformly magnetized sphere, then we know, this is some standard problematic Griffiths, what the magnetic field is associated with a uniformly magnetized sphere. Inside it's uniform, and then outside it becomes this dipole field, right? You remember that problem. So, near the origin. So if I thought about the nucleus as a uniformly magnetized sphere, then inside we have this so if we treat the nucleus as a uniformly magnetized sphere, then the B field inside is mu naught over 4 pi times 4 pi over 3 times the magnetization, where M is the magnetic dipole per unit volume. Now, if we take the limit and forget about the fact that this is a finite radius and ignore, in this context, the finite nuclear volume effect, then we take the limit of this as the radius of the sphere goes to 0, in which case the volume becomes a point. And the volume of a point is 0, so 1 over the volume of the point is a delta function. So we will write this as that. So there is an additional term here, which is, if I factor out now the magnetic moment, that's the spin, so this becomes 4 pi over 3 S dot I times the delta function at the origin. Okay, away from the origin, this term is 0. guess it's gotta be, it's minus, yeah, no, that's right, that's right.
It's like a correction to the Darwin term?
Sorry?
Like a correction to the Darwin term?
Well, it does in fact contribute with the Darwin terms, but in a different way, because the Darwin terms were independent of spin. So the Darwin terms cause an overall shift of the ground state. But as we'll see, this has a more profound effect, much more important effect, in changing the degeneracy and structure, absolute structure, and giving hyperfine structure to the ground state. The Darwin term just with some tiny shift. Yeah. It's actually bigger than this, but it doesn't affect the structure. Okay, so taken together, we have now and I've gotten some signs messed up somewhere and I can't find it. And I realize that my notes have, maybe it's right. Well, word to the wise, there's some errors in the notes that are posted on the hyperfine structure. I recognized them this morning when I was writing, when I was reviewing them, and I will repost those notes and let you know that. But what do we have? The total now we have is the magnetic spin for total proton spin hyperfine interaction. I'll call it HF, or hyperfine is equal to twice the G factor of the proton, the product of these. I'll put everything now in atomic units, factor out the distance or radius cubed, and then all of my radii and position will be in dimensionless units. This becomes L dot S plus I dot S minus 3 S dot E sub R I dot E sub R over R cubed plus 4 pi over 3 I dot S times the delta function at the origin. Okay. Put the hats on too when I do with an operator. All right, so this energy now is a perturbation to the energies associated with our now fine structure states. Remember, it was 2,000 times smaller. So we could first find the diagonalize and find the fine structure eigenstates, then use that as our zeroth order Hamiltonian and add in the hyperfine interaction. All right. So let's look at the effect on ground state of hydrogen. Okay, let's see what we got around here. Anything good?
There's a big one up there.
All right. So what's the ground state of hydrogen? Well, the ground state of hydrogen is the 1s, 1/2. Why is that true? Why is a half a good quantum number for the ground state? Well, that's J, right? Why is it a half? Because L is 0, and spin is a half, so it's the only J possible, right? And in this case, because L is 0, there's no coupling between spin and orbit. So these states are also product states of orbit and spin, because this orbit doesn't couple when the orbit is 0. So written in terms of all the quantum numbers, we have n equals 1, L equals 1 is the radial. This is my, L equals 0, sorry. This is my ground state radial wave function. Then we have the L equals 0, ML equals 0. That's my Y0, 0. And then we have M sub S. So S is a half. And M sub S equals plus or minus a half. However, now there's extra degeneracy beyond the spin of the electron, because now we got the spin of the proton. I mean, all of those states, all of the fine structure states, without thinking about how the nucleus affected anything, were doubly degenerate, because there was a nuclear spin up and a nuclear spin down, and the energy was completely independent of those two states. But now we're going to think about how the energy changes depending upon whether the nuclear spin is up or down. So we better include, I is a half, and M sub I is plus or minus a half. So this state is fourfold degenerate. Right? Everyone clear on that? So we have to do degenerate perturbation theory once again. And think about, we need to diagonalize our perturbation in the four-dimensional subspace associated with electron up, electron down, nuclear down, all the four combinations. Okay? Now, in the ground state where L equals 0, I should not have erased that, but oh well. So this first term, the L dot S term, is 0. There's no L. L is 0. So that term doesn't contribute. So then we have left over these two terms. So let's look at the matrix elements associated with that. So this I'll write now in atomic units. We have the fine structure constant squared, the ratio of the mass to the electron. So now writing everything in bar trees. And then we have I dot S. Just write it again. So, we need to diagonalize this, which means we need to think about the matrix elements of this operator in the basis that's described. Now, all of those basis elements have the same orbital. They all have the orbital. So in the 1s, 1/2 ground state, unlike what we were just talking about, the question Aaron asked about what are all the, there's only one YLN, Y00. And there's only one radial wave function, R10. So all of this one orbital. So all of our matrix elements are going to involve firstly, before I think about the spin, we can think about the orbital associated with what was I going to say? Yeah. So this is my 1s orbital. Right? And then ultimately we have to think about the spin terms, but everything is going to involve that kind of, every matrix element in the 4x4 matrix is going to involve this average over the spatial distribution. Now if I look at this is why I said I shouldn't have erased that picture. We had the magnetic field associated with the proton spin outside the nucleus was this dipolar pattern. And if I average this over the 1s orbital, I'm averaging something that's a dipolar pattern over a sphere. That average is 0. One way to understand that is that the dipolar pattern itself is Y1n. That is to say, this itself, the dipole pattern, is a YLN. The different components of a dipole are Y1, 0, Y1, plus 1, Y1, minus 1. And the average of one circle harmonic with a different circle harmonic will be 0. Okay. Another way of saying that is related to parity as well. So this term goes to 0. And all I'm left with is this term, if I'm in an S order. And this is what is sometimes called the contact interaction, because it depends on there being contact between the position of the proton and the position of the electron. So this then is equal to some constant we'll call A, I dot S. That's the only operator that's left. Doesn't you recognize that for our hyperfine interaction, which we use all the time? And what is A here? It's a constant. A is equal to 2 times the, in atomic units, the G factor, the fine structure constant squared, the ratio of the masses, times 4 pi over 3 times Y10, I'm sorry, R10, the origin squared, and the square of the YLN, which is 1 over 4 pi. it's, then you just have to figure out what that number is, which we will at the end. All right, so now we have a nice Hamiltonian to diagonalize. What we've done is we've averaged now over the spatial orbital, and we need to consider the spin degrees of freedom, the spin of the electron, and the spin of the proton. So, in the 1s, 1/2 subspace, we have 4 basis vectors. For simplicity, let me write them like this. Okay, where up and down are spin up and spin down for electron and proton. The proton, I put a little slash through it. Okay, so this is the electron, and this is the proton spin quantum number. Is that clear what that crazy notation means? Someone agree? All right. So what we need to do now is diagonalize this operator in the spaces, which we could do. We could do it in a very tedious way. We could write this as the x, y, and z components, write the x, y, and z components. Well, the z components, these are eigenstates of the z components, and then the x and y components are raising and lowering operators. We'd have to write it all out. We'd have to take all the matrix elements. We'd have to write out a 4x4 matrix and diagonalize it. But we shouldn't do that because we can see in the same way that we had the L dot S interaction, and we're able to diagonalize that just by I. Now we have an I dot S interaction, which we could diagonalize by going to the coupled representation. Just like we had with L and S. Now, the convention is, notationally, in atomic physics, we define F as the sum of the nuclear spin and the total electron angle length J. That's what F is. In this case, here when we're talking about it in the ground state of hydrogen, where L is zero, so it's also I plus S when we're talking about a state with L equals 0. So the coupled representation of I and S are the eigenstates, the good quantum numbers, so the mutually commuting operators. the magnitude f squared, the magnitude I squared, the magnitude s squared. Of course, each one of these is where the quantum number half, so those are fixed. And then fz. So the good quantum numbers here are f, m sub f, I is a half, s is a half. We typically don't write those because, we know that. We don't need to write it down every time. So those, I claim, are the eigenvectors, just like we had before. Why? Well, because this commutes with all of these operators. So this is a mutually commuting set that commutes with the Hamiltonian, and thus defines the eigenvalues. What are the eigenvalues? Well, to do that, you do the same trick you always do. You look at f squared. F squared is, in this case, in the context of the system with L equals 0, is equal to I squared plus S squared plus 2 I dot S. And thus, I dot S is equal to a half F squared minus I squared minus S squared. So what are the eigenvalues associated with the hyperfine perturbation in the ground state of hydrogen? Or more generally, a hydrogenic atom. Of course, for different hydrogenic atoms, this constant A will be different, but the form will be exactly the same. So the eigenvalues of the hyperfine Hamiltonian in the 1s ground state are the shift in the energy, the hyperfine energy, depends on F alone. Of course, I and S are fixed, but F can vary. And it's equal to A over 2 F plus 1 minus S plus 1 minus I plus 1. Let me write this just more generally, like that. In the context of hydrogen, S is a half, and I is a half, in which case each of these guys is 3/4. So this then is equal to minus is A over 2 F plus 1 minus 3/4. F plus 1. Okay, good. So, what are the possible values of F in the 1s 1/2 ground state of hydrogen? F is the sum of I and S. So F can be between I plus S in magnitude and I minus S. So what are the possible values of F for the ground state of hydrogen? One and zero, thank you, sir. So those are the possible values. And of course, there's degeneracy. And what is, so for F equals 1, we get A minus 3/4. So the shift is A minus 3/4 for F equals 1, And for f equals 0, the shift is, I guess, no, sorry, a over 2. The shift is minus 3/4. Okay? I say 4 over 2. It's confusing because.
Should still be proportional to A, right?
Yeah.
Oh, that's, yeah, thank you. Yeah, I'm sorry, yeah, so I screwed this up, sorry.
The brackets and the.
Yeah, that's what messed up, sorry. So, let me write this. That's what it is. So that's 3/4.
You factor the half in front.
No, but each one, the 3/4 and 3/4 add together to be 3/2. So that is correct, in fact. Okay, so then we get, for f equals 1, we get 4/2 minus 3/2, 1/2, so it's a over 4, and minus 3/4 a. That's good. That looks familiar. So, what we see here is that the 2s 1/2 round state, I'm sorry, the 1/2 round state, which was fourfold degenerate, now gets split into a manifold of states with f equals 0, there's only one, m sub f equals 0, and an m sub f equals minus 1, 0, and plus 1. And this splitting here in hydrogen is 1.42 gigahertz, a lot smaller than in cesium. Which is in wavelength 21 centimeters. So of course this is the source of radio astronomy. It's out there in outer space, you got this pretty cold hydrogen, it's pretty much in the ground state, but it could have this amount of energy around it. If some of those hydrogen atoms collide with one another, you can get an emission of this radio frequency photon. So this is what we call hyperfine splitting. Let me just quickly sketch here the excited states of hydrogen and put in now we can finally write down in some sense the real hydrogen atom, including all the important effects. I mean, there can be tiny effects due to, coupling to the weak field, but these are the dominant effects that are resolvable in terms of the splittings. So, the real hydrogen atom. So we said we have the 1s 1/2 round state, which got split up into an f equals 1 and an f equals 0 hyperfine manifold. We have the excited states now. This is all the n equals 2 manifold, where we have the 2p 1/2 now gets split up into an f equals 1 and an f equals 0. The 2s 1/2 gets split up as well. in terms of these. Be done in one moment. And you can go ahead and get started.
Just don't use this door as well.
Okay. And now I ask you, what are the possible values of f in the 2p3 halves? Well, j in this case is 3 halves, and the nuclear spin is 1/2. F was j plus I. So I can have 3 halves plus 1/2, which is f equals 2. And f equals 1. Okay. In this case, the hyperfine splitting, the ratio of hyperfine splitting in the excited state to hyperfine splitting in the ground state, it's about a factor of 1/3 less. We'll talk about this for other atoms like alkali atoms where the ratio is much different, where the ground state splitting is huge compared to the excited state splitting in terms of the hyperfine splitting. Could be, factors of 20. Sort of depends on the alkali. And then, of course, each one of these states has m sub f magnetic sublevels within them. In this case, I would have a 5-fold degenerate manifold, a 3-fold, 1-fold, etc., etc. And those levels could be split in the presence of a magnetic field, for example. All right. So we're finally done with hydrogen, and next week we'll start talking about multi-electron atoms. All right.